Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hello everyone. Okay, so today we're going to discuss about topic 5, electromagnetic induction. Okay, so given in the picture is the application of electromagnetic induction in our daily life. For example, we use what we call Apple Pen to write on our tablet. Okay, we used to swipe our card on the grocery shops. Okay, or in airport we have a screening to detect either we have a metal or not. That one is also an application of electromagnetic induction. Okay, so for topic 5 we have six subtopic. Okay, so we need to finish it before your mid-sem break. Okay, so for the first subtopic, we're going to discuss about magnetic flux. We're going to define what is the definition of magnetic flux and how to use it. Okay, so as we know, when we have a magnetic field, then that's mean the magnetic field will come with the magnetic field lines. Okay, so the number of magnetic field line passes through an area, or what we call it as a plane. So the number of magnetic flux, or how much of it, that's what we call it as magnetic flux. Okay, so this one here, this is should be magnetic field, it's not electric field. Please correct it in your lecture notes. Okay, so by number of magnetic field line passing through an area or a plane, that's what we call as a magnetic flux, and it known as a scalar product between magnetic field strength vector and the area of the surface. Okay, so in order to determine the magnitude, okay, so we know that magnetic flux represent by the symbol of phi. So this one is called as phi is equal to vector magnetic field dot with area. Okay, so we know here they use dot product. Okay, so dot product basically it represents scalar. So when it presents scalar means both product must be in parallel to make it maximum value. Okay, so how to determine the magnitude of magnetic flux? So we can just add another cos theta at the back. So it will be BA cos theta. So how to determine the angle of the magnetic flux? So the angle should be determined from the normal of the plane to the magnetic field. Okay, not from the plane to the magnetic field. It must be determined from the normal and magnetic field. So if you get this question regarding magnetic flux, first thing first, you need to draw a diagram and determine the direction of the normal of the plane. Okay, then afterwards you will know what will be the suitable angle you need to put in your calculation and get your correct answer. Okay, so for this, the SI unit, okay, will be Tm squared. Okay, here Tm squared, Tesla meter squared. Okay, or we can use it as Weber, so as simple as that. Okay, all right. So for magnetic flux, okay, oh sorry, saya tak perasan, tak padam, tak apalah. Okay, alright. So kita tengok dekat sini, we have a three different position of plane. Okay, so the first one is the maximum one, when the normal of the plane is parallel to the magnetic field here. Okay, that's when we put our angle as 0. Okay, so same for the second one, or the normal is parallel but the direction is in the opposite direction, so your angle will be 180. Okay, so your maximum will get a negative value, but it's still correct. Okay, either 0 or 180. And the third one, it looks like the plane is parallel to the magnetic field, but remember, we need to determine the angle from the normal of the plane. That means the normal and the magnetic field is equal to 90 degrees. So cos 90, you will get 0. So if it happened to be in this position, plane and magnetic field is parallel, then the magnetic flux will be equal to 0. Okay, kenapa kita nak plane ni berada pada kedudukan 90 degree to the magnetic field? Sebab kita nak magnetic field tu pass through kepada plane. Okay, bukan kalau dia tak pass through means kalau you punya plane horizontal dan you punya magnetic field pun horizontal. So dia tak ada intersect. Okay, so bila tak ada intersect maksudnya you tak akan hasilkan magnetic flux. You tak akan menghasilkan pemotongan of magnetic field. So tak kata hasilnya lah magnetic flux. Okay. Alright, so if the case that you have more than one turns, alright, so what will happen? Okay, if you have more than one turns, then we call it as magnetic flux linkage. Okay, so it means one plane, one coil is magnetic flux. If you have more than one, let's say you have 100 number of turns, then it will become 100 times the magnetic flux for one coil. Okay, so you just add on another NA, which is this is a number of turn of the coil. Sebab dia kena kira satu-satu. Maksudnya berapa plane. Contoh kalau kita ada 100 coil, so maksudnya kita ada 100 plane yang magnetic field to pass through. Okay, so magnetic flux tu dia hanya consider untuk dia pass through satu plane sahaja. So if you have 100 turns of coil, means you have to consider the magnetic field is across 100 number of turns. Then it will call as a magnetic flux linkage. How about the unit? Still the same because you only multiply with the number of turns. Okay, but remember the angle must be between magnetic field and the normal of the plane. Okay, next. So how do we determine Faraday's and Lenz's law? Okay, as you can see from the diagram, so we have a magnet bar here, and then we have a solenoid. Sorry, we have a solenoid. Okay, and then we have a galvanometer. Okay, the galvanometer here is to detect the current flow. Okay, as you can see, as the magnet bar move towards the solenoid, there's a deflection at your galvanometer, either to the left or to the right. But remember, the deflection of galvanometer is in the opposite direction of the direction of current. Okay, so what we are trying to explain here. Okay, wait for a while. Okay, what we are trying to explain here is that electromagnetic induction produced by the changing of magnetic flux across the coil ataupun current carrying conductor. Okay, so maksudnya bila ada relative change means bila ada movement of magnetic field across a plane, then you akan hasilkan magnetic flux, betul? Okay, tapi sekarang magnetic flux yang you hasil berubah-ubah bila ada pergerakan. Okay, so that means Faraday kata magnetic flux is equal to, sorry kat sini magnetic flux is equal to rate of change of magnetic flux. Induced EMF is equal to the rate of change of magnetic flux sebab dia ada perubahan kepada magnetic flux itself. Okay, dan kenapa ada negatif? Negatif ni adalah hasil kajian daripada Lenz's law. So dia kata the direction of induced current ataupun induced EMF is in the opposite direction. Okay, so maksudnya dia terbalik. Sebab tu dia jadi negatif. Ini apa yang Lenz's law bagi tahulah. So direction of induced EMF ataupun induced current is always in opposite change in magnetic flux that cause it. So maksudnya kalau contoh, okay, kita bagi contoh, kita tengok sini macam mana kita nak hasilkan induced current. Okay, kita tengok yang pertama ni. Ni yang saya dah lukis lah. Okay, so let's say kita yang tadi tu kita ada North Pole dekat sini. Okay, so bila North Pole tu approaching the solenoid, so basically solenoid ni tak ada apa-apa current flow. Tapi dia terhasilnya current bila ada movement of magnetic field. Okay, sebab dia ada cutting of magnetic flux. Cutting of magnetic field across the plane, so dihasilkan magnetic flux. Dan magnetic flux tu berubah sebabnya ada pergerakan. Okay, so bila dia approaching, okay, so automatic pada solenoid ni dia akan menghasilkan magnetic field. Okay, kita panggil dia sebagai induced magnetic field. Okay, tapi ke mana arah induced magnetic field? Okay, itu yang kita nak kena figure out. Alright, so bila dia approaching, sebab kita nak berlakunya relative change. Okay, bila dia approach maksudnya kita nak dia tolak kembali sebab kita nak dia ubah arah kan. Okay, means bila dia datang with a north pole here, pada induced magnetic field dia kena hasilkan magnetic field yang sama. Sebab bila kita hasilkan magnetic field yang sama, same pole, dia akan repel lah kan, betul tak? Okay, so ni apa yang berlaku lah. So bila kita dah determine direction of magnetic field, okay, by using your right hand grip, so kita boleh determine direction of induced current. Okay, so kena determine direction of induced current dulu. Pada kita punya solenoid, baru kita boleh determine direction of induced current. So kalau kita tengok dekat sini, dia datang daripada kiri ke kanan, betul? Tapi sebab dia adalah bacaan pada galvanometer, so deflection dia akan jadi terbalik lah. So deflection of current will be deflect to the left instead to the right. Okay, this is what happened when the magnet bar approaching the solenoid. Okay, what will happen if the magnet bar is moving away from the solenoid? As I told you before, kita nakkan perubahan pada dia punya movement. So, bila dia moving away, so kita nak dia datang balik. Okay, maksudnya kita nak tarik dia balik so that berlakunya pemotongan lagi of magnetic flux. So, bila dia moving away, magnetic field induced ni akan bertukar arah. Maksudnya instead of tadi yang jadi north kan, so bila dia move away dia akan jadi S. Sebab apa? Bila north bertemu dengan south, so different pole, so dia akan attract. So dia nak attract balik magnet bar tu untuk dia cutting the magnetic flux lah. So kalau kita tengok dekat sini, kita dah determine direction of magnetic field by using right hand grip. So sekarang magnetic field kita ke kiri, so kita punya direction of induced current akan ke atas. Okay, so kalau kita tengok dekat sini, direction induced current daripada kanan ke kiri lah. So sepatutnya galvanometer ni kalau ikutkan dia punya pergerakan ke kiri lah kan, betul tak? Tapi sebabkan deflection of galvanometer ni dia in the opposite direction, so dia akan pergi ke kanan lah. So sepatutnya ke kiri, tapi sebab dia akan oppose direction tu, so dia pergi ke kanan pada bacaan galvanometer. Okay, so daripada situation ni kita kena faham beberapa perkara, iaitu yang pertama dia mesti ada changes in relative motion. Maksudnya magnet bar tu mesti bergerak. Kalau dia tak bergerak, dia tak akan ada pemotongan of magnetic flux. Okay, bila tidak ada pemotongan magnetic flux, maksudnya takkan terhasillah induced magnetic field, current and induced EMF. Okay, so kenapa kita nak ada changes? Kenapa nak kena ada movement tu patah balik? Sebab kita nak cutting of magnetic flux. In order afterwards dia akan menghasilkan induced magnetic field. From that barulah terhasilnya induced current dan induced EMF. Okay.